so the motivation for this talk is how can we exploit product structure in polynomial optimization problems? So by exploiting, what does it mean? So it means that we want some sort of computational tractability in like approximation. So because products of different polynomials usually have very high degrees, that's why by standard methods, it slowly becomes computationally intractable very quickly. And we also want provable approximation guarantees. So this is what we set out to hope to achieve. And now let's introduce the problem, the essay problem that we are studying. So here we are given D matrices, A1 to AD, the PSD matrices. And we want to study this following polynomial optimization problem on the domain, which could either be real or complex numbers. So the objective is to optimize the product of these PSD forms of and here we'll also introduce a normalization factor of the power of 1 over d, but is equivalent to a polynomial of high degree polynomial optimization problem. And we are optimizing it over the sphere. Okay, so it turns out that this problem is a high degree polynomial optimization problem. It's a degree 2d in n variables. And however, this problem has a compact representation in that it can be represented by these D matrices, A1 to AD. So it can be represented in relatively low number of like variables. Like it can be represented in polynomial space. So so it turns out that when D is fixed, this problem has a polynomial time solution. But when D is, say, a constant multiple of n, this problem becomes NP hard. So in this talk, we'll be focusing on this problem, but the method of relaxation introduced can also be generalized to products of non-negative forms. All right. So what are some applications or like some instances in which this problem come up in? So one simple example is Kantorovich inequality. It comes up in the analysis of gradient descent on quadratic forms. So this is where, given some positive definite matrix Q, we're trying to maximize this objective over the sphere. So it's x transpose qx times x transpose q inverse x. So this corresponds to our objective in the case where A1 is q and A2 is q inverse. And it turns out that this objective, but Kantorovich inequality upper bounds this quantity by the smallest and largest eigenvalues of q. And this is one instance in which this product comes up. Another instance it comes up where this A sub i's are rank 1 matrices. So they're, say, VI transpose. So when these are rank 1 matrices, the objective becomes a product of linear forms. So, and this objective here is actually very closely related to permanence of PSD matrices, in particular the PSD matrix, which is the Gram matrix formed by these vectors, VI's. So I'll not go too much into it, but it turns out this objective is a lower bound on the permanent and can be used to approximate this permanence. And that's another work of me and Pablo. And the next special case, I guess, is when these AIs are diagonals. And in this has the interpretation of being a portfolio optimization. So you're supposed to given this rates of returns over a time period, and you want to maximize expected profit. This turns out to be sort of a geometric mean because these rates compound, and you want to. So here you can make the substitution yi equals to xi squared, and here you get the this product of linear form in this Ri. So it's another special case and of this objective. And there's a few more applications which I don't have time to go into today. And so, so what are our contributions, right? So since this is optimization, it's a polynomial optimization problem, we can use like standard semi-definite programming-based like relaxations or approximation algorithms, which is like called the sum of squares. And this involves SDP with O of m plus d choose d variables or constraints, and the approximation factor that it gives is omega 1 over n. So since it's a maximization problem, you want the approximation factor, the closer it is to 1, the better. So 1 over n is not as good. So, but for this particular problem, the product of PSD forms, we can show that this relaxation approximation that exploits this compact representation involves solving a much smaller size SDP, and it only has n squared d variables or constraints. And we can actually get a constant factor approximation for this problem. Yeah, so, in addition, well, we show that when d is a constant multiple of n, this problem is even NP hard to approximate. And we also introduce some higher degree relaxations, so which increases this number of variables or constraints, but it trades off the computation with approximation quality. So it gets more, it becomes computationally harder, but the approximation also becomes better. And finally, we also show that, okay, so how good is our analysis of this approximation factor? Can this even be better for our SDP relaxation? So show that there are integrality gap instances. We show that our analysis, this constant here that we get, is essentially tight. So what is this relaxation? So here it is. So at first we have this the optimization problem. And there are two ways of looking at this relaxation. The first one is using a rank 1 relaxation by essentially writing this x AIX to be the inner product of A with X transpose. This is very standard. And showing that, okay, so X transpose can be relaxed into this big matrix X, which is PSD and has trace 1. Right, so it turns out that this is a this rank 1 relaxation gives you the following SDP. And there's another way of looking at this, which involves using the AMGM inequality. So the second way is to use AMGM to bound this, upper bound this objective. So this can be upper bounded as the sum, or the arithmetic mean of sum of I plus 1 to d of the individual terms. So X, AI, X. All right. So, and it turns out that since we have some freedom to introduce extra variables, and this freedom is given by this alpha i's. So if you introduce this alpha i's, whose product is equals to 1, the initial objective wouldn't change, but we are also able to optimize over these alpha i's to find the best ones to give us the best in upper bound. And so this optimizing over these alpha i's can also be written as the following SDP here. And it turns out that these two are dual to each other. So two separate ways of looking at this relaxation. And yeah, so the theorem that we have is that, okay, so let X star be the optimum of, say, of this SDP here. And we have some constant, this gamma to be some constant, and this phi be some digamma function. And this constant approximation factor that we get from here depends on the rank of the optimum solution. And it's given by this function over here. So it turns out that, so how does this relate with R? So even if R is really big, this expression is still lower bounded by a constant. But if R gets smaller, if you can show that the R is smaller, there's a low rank solution, then this approximation factor will improve. In particular, when R is 1, if there's a rank 1 solution, it means that the problem is exact, and here the C of R also becomes 1 in this expression. So this is what we expect as well. All right. So so just to give a short proof sketch, how do we do this, right? So we start by defining a rounding algorithm. So given this optimum solution, we can produce a feasible solution. Given the STP solution, we want to produce a feasible solution by first sampling from the normal distribution and then normalizing the vector. So this is very standard as well. And the interesting thing comes in the analysis, right? So in the analysis, we know that the optimum is lower bounded by this expectation. Expectation is over the randomness of the rounding algorithm, and this can also be written in the form in this equivalent form. But we can also bring the expectation in using Jensen's inequality, so which lets us analyze each term one by one. So after some more calculations and a few more tricks, we obtain this this constant vector that we showed I described like in the previous slide. And this is just a proof sketch. And so next, so this analysis is actually quite nice, and this leads to another application or interpretation of this result. So here, so it's called the convex Hall of the image of a quadratic map. So first we define a quadratic map phi, which is a map that maps any x in Kn to another vector in sorry, I think this should actually be R of D. I'm sorry, this is R of D. And this is done by these D quadratic forms that we're provided with. And the natural question is to ask, when is this image of the quadratic map convex? The image of the Kn under this quadratic map, when is this convex? So it turns out that if you have only two quadratic forms, so your the output is a two-dimensional vector. This is true, and this is related to the S lemma, and it's related, yeah, and related lemma for the complex case, but it's not true in general. It's not always true that this image is convex. So the next question, natural question is asked, well, how far is this image from its convex Hall? But there's many different ways of measuring this distance, but one way is to measure this relative entropy distance. What's the relative entropy distance between, so it turns out that also this image and its convex Hall, they are all cones. It's quite easy to see that they are both cones. So we take these cones and we intersect them with the simplex. And from this intersection, you get some complex set, and of which you can measure the distance between them. And it turns out that this rounding method that we have above actually gives us a way to upper bound the relative entropy distance. And it shows that, well, this relative entropy distance is upper bounded by the log of the same constant we have from before. And this result actually is proven by Parrilo for a larger constant, but our analysis, as well as the integrity gap that we exhibited, show that this is essentially asymptotically optimal. So this constant over here that we get. Okay, so there's another way of interpreting the results. And so the next part of the talk, we talk about some higher order relaxations. Like, can we somehow trade off between computation and relaxation quality? So so as we talked before, this relaxation can be interpreted as using the AMGM inequality to find the best upper bound. But can we get a better bound with something better than the AMGM inequality? So these exist, and first we start by defining this elementary symmetric polynomials, and this and also Maclaurin's inequality, which is a kind of a generalization of AMGM inequality. So here is the left-hand side is the geometric mean, and there's a whole bunch of intermediate inequalities which involves the elementary symmetric polynomials. And at the right-hand side, you get an arithmetic mean. So we can, instead of using this AMGM inequality in our relaxation, we can use this intermediate inequalities to construct these intermediate relaxations for this K between 1 and D. So what we had before this opt of SDP, we can call it opt of SOS1. And we have from using this strategy, we get opt of SOSK for K from 1 to D. So what this does is, of course, is trade-off computation for accuracy. So next, end with an example. This example is called the Icosahedral form. So this is the picture you saw in the first slide. So this is a polynomial in 3 variables in and of degree 12, and it's also can be written as this product of PSD forms because it's a product of squares of linear forms. So what does this polynomial look like? It looks like this. It's a polynomial on the sphere. So on the sphere, it looks like this. Has its optimum on the vertices of the icosahedron, and it is it turns out to be a very hard instance because of the high degree of symmetry. So in particular, if you want to just use our SDP-based relaxation on this, the resulting rounding algorithm just tells you to sample a random point on the sphere. Because of the symmetry, it doesn't get any special information from just the SDP relaxation. But another question is, with this higher order relaxations, can we do better? So from these intermediate relaxations, we can also implement randomized rounding algorithms to obtain some feasible solutions from the relaxations. So this randomized rounding algorithm tries to take in the solution to these intermediate relaxations and produce a feasible point. Okay, so how does this perform? So I show some numerical results. So remember what this polynomial looks like, and here's like a projection of it onto the plane. So the contour line shows the optimal values of this polynomial, and you can see there's about 12 optimum points, and this is of course the equal area plot. Okay, so and the dots show the sample points from the rounding algorithm. Here is when k equals to 2. So you can see that when k equals to 2, the rounding algorithm doesn't seem to be producing much, right? It seems to be just sampling random points on the sphere. But what happens when we increase k? When you go to k equals to 3, rounding algorithm seems to be, the distribution from this rounding algorithm seems to be like concentrated more towards this actual optimum. And this is true when we increase k even more. K equals to 4, k equals to 5, and k equals to 6. And you can see that, and here's this comparison between, let's say, k equals to 2 to 6. You can see, of course, like the distribution concentrates towards the optimum as k increases. All right. So what's the takeaways of this talk, right? So this product of PSD forms has really nice structure, where it generalizes many problems. And using this nice product structure, we can write computationally efficient relaxations, and also we can prove good approximation guarantees for these relaxations. Of course, some interesting things to think about is, since our approximation factor depends on the rank, if we can show that in some instances, because of symmetry, we can guarantee a low rank solution, then we can also guarantee like a better approximation factor. Also, like, can we also generate these like intermediate relaxations for other like high degree optimization, polynomial optimization problems? That's another thing to think about. All right, so that's all I have. So any questions?
Thank you. Are there any questions or comments?
Hi, Chenyang.
Hi.
I have a question.
Mm-hmm.
So your your one way to generate your relaxation is with this like a AMGM inequality, right?
Yeah.
And this reminds me of the like Sage relaxations, like from Venkat, or the songs relaxations. Like I was wondering if there is a connection between your relaxation and Sage.
Yeah. So that's an interesting question, right? Because I think, yeah, I've looked into it, but it doesn't appear there's like a immediate like connection. But and the nice thing about this this AMGM like is it allows us to like get a really proof like approximation guarantee, and I think that's the main reason why we use this. Yeah. Okay.
Okay, thank you.
Thank you. Yeah.
So what do you mean by low rank guarantees of solution from symmetry?
Yeah, so I have a very concrete example actually. So so it's actually in the other in this paper where so just say for example where this so where the A sub i's are, so in the permanent case, for example, if this matrix M is circulant, then you can guarantee like that the solution is of a low rank, like maybe rank 1 or 2. So this is actually written in this paper. So that's one particular example. So when this matrix is circulant, then
okay, but the kind of result you're hoping for is what? Something about the symmetric group, and based on the symmetric group, you would then guarantee a low rank solution of some sort, something like this?
Yeah.
That's the kind of result you're looking for?
Yes.
Okay.
Yeah, in particular, for like in the circulant case, these A sub i's are simultaneously diagonalizable.